So we've been looking at limits for a very, very long time. And before we even got into limits, we started looking at average rates of change, which were rates of change. We could find the secant line between 2 points on a curve. And then we also talked about instantaneous rate of change. What was that rate of change at a particular value? And that was on our tangent line. And so in front of us, we have the same graph, and we have 2 points on that graph, and we want to use the grid and a straight edge to make a rough estimate of the slope of the curve at points 1 and points 2. Okay, so let's look at the graph. If you're looking at the graph and looking at point 1, I can see, first of all, that my function is decreasing, right? It's going down from left to right. So first of all, that should tell me that I know that my slope of that line, I should be getting back a negative number. But we want a straight edge, and we want to try to figure out and make the tangent line. So the tangent line at that point, so we're going to line it up, is about like this. And so I'm going to just draw this line in here. And maybe I'm off a little bit, but it's, I think, kind of close. So right here, that was our point 1. And we want to find the slope of that line. And so we want to choose 2 points on that line. And so maybe we should choose the point that's actually there. Or we don't actually have to. Let's choose points that actually are at integers. That might even make our life even easier. So what about this point right here? So there's a point on that line, which was -2 for x. And I guess that's not a whole number. Looks like 1/3 for y. Okay, so let's choose another point on here. So it looks like it's intervals of 3 in between. And so this here is an x value of -1. And my y value here is -2 and 1/3. And so I want to find the slope between those 2 points. And we know it is equal to the change in our y value. So -2 and 1/3 minus the other y value, 1/3, all over -1 minus -2. So -2 and 1/3, let's rewrite that as a mixed number. And so if we rewrite that as a mixed number, that is -3 times 2 is 6 plus the 1. So this is -7/3 minus 1/3. All over, and minus a negative, so really it's plus in here. So you have -1 plus 2, which is just 1. So -7/3 minus 1/3, that's -8/3 over 1 is -8/3. So we can see that that slope in there is approximately -8/3 by taking a straight line. And that would be at the point P sub 1. Or another way to say that, the slope of the tangent line at that P sub 1 value. So looking at it, they want to do the same thing with P sub 2. Give myself some more room. So P sub 2, if we look at P sub 2, it looks to me like that is actually a maximum value at that point. And so here, and that's a curve, it's not a sharp corner. If I look at this, the tangent line is actually horizontal. And I could choose 2 points on that line, but I also remember that horizontal lines have a slope of 0. Because our y value is the same, so the change in our y value is going to give us 0 over a different x value. A 0 over a number is 0. Okay. So we can estimate what the slope is at a particular curve, especially if we're given a grid like that, and we can make the tangent line that goes through it, find 2 points, and find the slope. Let's say we're given a function and we want to find what the equation of the tangent line or what the slope of the tangent line is at that point. Okay, so by definition, we can say that the slope of a curve y equals f of x at a point P, and let's call it x of 0 is our x value, and so our y value, we would plug that in wherever we saw an x in our function, and we can say f of x sub naught is the y value, is the number when we find the limit as h goes to 0 of f of x sub 0 plus h minus f of x all over h. We have to state provided the limit exists. It's possible it doesn't exist, and we'll talk more about that later. So the tangent line to the curve P is the line that goes through P with this slope. And we were finding equations of tangent lines in the past. First section of chapter 2 in our textbook. Okay, notice this next definition, almost identical to what we just had right here. Let me just read through this really quickly, and then we'll look at some examples. Oops. So rates of change. Another way to say this, the derivative at a point. So this expression, and we've worked with this before, f of x of 0 plus h minus f of x 0 over h, as long as h doesn't equal 0, is called that difference quotient of f at x of 0 with increments of h. If the difference quotient has a limit as h approaches 0, that limit is given a special name and notation. Here's our derivative. So the derivative of a function of f at a point x of 0 denoted by, you can't see it, it's f, there's a prime here, a little dash, and then x of 0. So it's denoted by, and I read it as f prime of x of 0, or the derivative of f at x of 0 is given by the limit as h approaches 0 of f of x of 0 plus h, all of that minus f of x of 0 all over h, provided the limit exists. So the point I'm trying to get to is that there's different ways that we can say pretty much the same thing. So I just want to state that right now, and like I said, we'll go and get into examples. So we've been discussing slopes of curves, lines of tangents of curves, rates of change of functions, and derivative of a function at a point. All of these ideas are based off the same limit. So the following interpretation of the limit, that difference quotient, as h goes to 0, that difference quotient, I'm not going to read that off again. We can say that this is the slope of the graph of y equals f of x at x equals x of 0. We can say it's the slope of the tangent line of the curve y equals f of x at x equals x of 0. We can say it's the rate of change of f of x with respect to x at x equals 0. And we can say it's also the derivative f prime of x of 0 at x equals x of 0. So instead of saying rates or instantaneous rate of change, we're going to just call it rate of change now. Which is different than the average rate of change. If it has the average rate of change there, then that's not the derivative, that's the slope of the tangent line. So if you don't have that average in front of rate of change, it's talking about the derivative or the slope of the tangent line. So let's look at some examples. So this example says find the equation of the tangent line y equals 1 over x squared when x equals -1. So we want to, a couple of things, we need to find a point and we need to find the slope. So one thing, we can find the point. If we go back into our original function, I'm going to call f of x, and we plug in -1 wherever we see an x. And when we do that, we get 1 all over -1, and then we're going to square that. So we get 1 over 1, which is 1. So we know we have a point, -1, 1 on f of x and on the tangent line. At x equals -1 on f of x. So now we need to find that slope, and we can find that slope by looking at the limit. So we know that f prime at -1, this is going to equal the limit as h approaches 0. I'm going to first write it like this. F of x sub 0, so our -1 value in this case, plus h minus f of -1 all over h. So this wants us to go in, and it wants us to plug in -1 plus h wherever we see an x in our function. So let's bring down our limit because we haven't taken it yet. And we're going to need to go through here. And if we did take it right now and just did our direct substitution, we would get that indeterminate form of 0 over 0. So we can't take it yet. So let's go in and we're going to plug in -1 plus h wherever we saw an x. And square it. Minus f of -1. We already found f of -1, didn't we? So f of -1 we found was 1. So minus this 1 all over h. I'm still getting this 0 over 0, because if I plug in 0 here, that first term, that fraction, would have given me 1 over -1 quantity squared, which is +1. So 1 minus 1 is 0 all over 0. And so this is where we're going to use our tricks of getting rid of that indeterminate form. One of them was, if we had a complex fraction, which we do, was to get rid of that complex fraction. And so look at your least common denominator. Notice our denominator there is -1 plus h. That's our least common denominator within this fraction, that main fraction. So we're going to multiply by the LCD. So -1 plus h quantity squared, both to the numerator and denominator. And so when we distribute to the first term in that numerator, our fraction goes away and we're just left with 1. I haven't taken the limit yet, so I'm bringing it down. And we get 1 minus, so distributing this to the 1, nothing cancels. So I have in here -1 plus h quantity squared all over h all times -1 plus h quantity squared. We're going to need to do a little bit of work, and maybe we can do it over here on the side. So if I FOIL out -1 plus h times -1 plus h, because that's what that quantity squared is telling me to do, and do all that work, I get -1 times -1 is +1. And I have -h and minus h, so that's -2h. And h times h, so plus h squared. But I technically have this minus in front of that. So if I put a negative in front of that, I'm going to have to distribute that negative inside of every term. So if we do that, we get back -1 plus 2h minus h squared. So let's write that in. So I have 1. I already did all the work. So I've already subtracted it off. So this would be -1 plus 2h minus h squared all over our h. I'm not going to distribute this out down here. So -1 plus h quantity squared. So I noticed that I have a 1 minus 1 in my numerator. Those two values cancel out. I also notice, again, if I go in and plug in 0 for h, I still get that 0 over 0. I also notice now what's left in my numerator, I have a factor of h in common. So I can pull out an h from both of those terms left in the numerator, and that can cancel with the one I have down in the denominator. So if I factor out an h in the numerator, we're left with 2 minus h all over h all times -1 plus h quantity squared. Now we're good. If we go in and do our direct substitution and we go in and plug in 0 wherever we see an h, we're not going to get that indeterminate form anymore. So we have 2 minus, I see an h there, replace it with 0, all over -1 plus 0 quantity squared. So I'm left with 2 in the numerator, all over 1 in the denominator, which is 2. So we just found that the derivative of our function at x equals -1 is equal to 2. So this is the slope of our tangent line, m is equal to 2. At that point, -1, 1. And so now that we have a point and we have the slope, we can find the equation of the line. Okay, so we have both of the things. We have our slope and our point. And so it depends on how you want to do it. I tend to like the y equals mx plus b. Let's plug those values in. We'll just be left with b, and we can figure out what our y-intercept is. So I have a point when x was -1. My y value was +1. We saw our slope was 2. Plus b. So I get 1 is equal to -2 plus b. Add 2 to both sides, we get b is equal to 3. So the equation of our tangent line is y equals our slope, which is 2 times x plus b, so +3. Okay, so if we graphed that function, I can tell there's a vertical asymptote because of the x squared value. That's x equals 0, sets the denominator equal to 0, but not the numerator. So I know I have a vertical asymptote on my y-axis. I also notice that if I look at the limit as I go to positive and negative infinity, 1 over infinity, it's going to be positive on the bottom, that's going to be going to 0. So I also have a horizontal asymptote. We could talk about the limit as we're approaching 0 on the left. Well, because I'm squaring it, it's going to be shooting upwards to positive infinity. So my graph is going to look like this on the left-hand side of the vertical asymptote at x equals 0. And on the right-hand side, same idea. That's going to be going off to positive infinity. If you look at this, at x equals -1, and I don't have this to scale. If you look at this, notice that if I draw my tangent line through -1, x equals -1, I can see that that graph is increasing, that tangent line is increasing from left to right. So it's a good thing I got that was 2. And it's not, but I would have something that looks like this, graphing both my tangent line and my function y equals 1 over x squared. So same graph that we were just looking at that we did by hand, I just put on Desmos. And so in red, we have 1 over x squared. That's what we graphed. We found our tangent line, y equals 2x plus 3. That's going through that point at -1, 1, which we found. I'm not sure. And it looks like the tangent line right there. If you zoom in, you can tell that that's what the tangent line would look like there. So our next example says, find the equation of a line having a slope of 1/4 that is tangent to the curve f of x equals the square root of x. Okay, so we need to find the point or points on this curve, y equals the square root of x, that has a slope of 1/4. And so we need to look at the limit as h approaches 0. Maybe we can say, let's assume this occurs at x equals a. We'll figure out what a is. Okay, so I'm going to find the equation of the tangent line I know is going to have a slope of a quarter at x equals a. So I'm going to put that in there. So I'm going to look at f of a plus h minus f of a all over h. And we know we're trying to find out when is this equal to a quarter. So we need to go into our function f of x. And we need to plug in a plus h wherever we see an x. And so I'm going to bring down my limit as h goes to 0. F of a plus h, that's a square root. Plugging in a plus h where I see an x, so square root of a plus h minus, well, f of a, so I'm going in, I'm plugging in a wherever I see an x. That would be the square root of a all over h. Again, we want to know when is that a quarter. Let's ignore the quarter for a minute because I need to do some manipulation on this. And so that's just going to get in the way for a second. If we go in and we plug in 0 for h, we get that 0 over 0. So we got to do our manipulation. We have radicals in here, and one of the tricks we learned was that we can multiply by that fancy one, the conjugate, in this case of the numerator. And so we can multiply the top and the bottom by, change the sign in between those radicals, the square root of a plus h plus the square root of a. We're causing this to be a difference of squares in here. And so since that's a difference of squares, when we take the square of the first term, the square root of a plus h, that just gives us a plus h, minus the square of our second term, so square root of a quantity squared is a, all over h. I'm not going to distribute this. I'm just going to leave it as a square root of a plus h, and then plus that square root of a. So notice we made this so that a minus a cancels. Those cancel. Notice that I'm just left with an h in my numerator, and I have a factor of h in my denominator. So notice those cancel. So technically, I have the limit here as h goes to 0 of 1 all over the square root of a plus h plus the square root of a. And so now if we go in and we do our direct substitution and we plug in 0 wherever we see an h, this is going to give us 1 all over the square root of a plus the square root of a. Those are like radicals. We can add them together. So 1 root a plus 1 root a is 2 root a. So we want to find out when is this limit equal to a quarter. So when is 1 over 2 root a equal to a quarter? So I need to solve this equation. I notice it's a fraction equal a fraction, so we could do cross multiplication. Same thing as saying, well, let's just multiply to clear our fractions. If I look at the LCD of 2 square root of a and 4, that would be 4 root a. So I could multiply 4 root a on both sides. My equation. And so that would leave me with 4 root a times 1 over 2 root a. Square roots of a cancel, 2 goes into 4 twice. So that leaves me with 2 on the left. And square root of a on the right, because the 4's cancel. I want a, I don't want root a. And so we can get rid of the square root by squaring both sides of our equation. And so this would give me a would have to equal 4 then. So the equation of the tangent line that has a slope of 1/4. We don't have that equation yet. We know what x value it occurs at when x equals a or x equals 4. So let's find a point. At x equals 4. So if I look at f of 4, plug in 4 wherever you see an x, we get the square root of 4, which is 2. So we know our point is at 4, 2. It gave us what our slope was. Our slope is 1/4. We just had to figure out what point that was at. And so now we can find that equation of the tangent line. So you can use your point slope formula or plug it into your slope intercept form and find out what b is. So for our point, y is 2 is equal to our x value, which is 4. Whoops, our slope, which is 1/4. Times our x value, which is 4, plus b. So I get 2 equals 4 times 1/4 is 1 plus b. Subtract 1 on both sides to get b by itself. 2 minus 1 is 1. So we know what our b value is. We were given our slope. So we have our equation of the tangent line. Y is equal to 1/4, 1/4 times x plus b, which is plus 1.